This video is going to show you two different things. One is how to solve one of the problems that was on the quiz last week, and the other is to model how you should be preparing your homework solutions. I've been looking at homework 2, the first one you turned in, and I kind of got stopped because a lot of people weren't paying attention to the guidelines. I want to show you how you would do that. Every problem should start off with a sketch if needed. We've got that. And then the given and to be determined. And so I'm going to write out the given and to be determined here. So here is the given. I've tried to summarize all of the crucial details here. We've got a 2.53 kilogram block on a plane tilted at 36.5 degrees, connected via a frictionless pulley to a hanging block. Static friction on the plane has mu sub s equals 0.43. That's the statement of the problem. Now, to be determined. The minimum mass for block 2 to overcome static friction and pull block 1 up the plane. Now this is a fairly long given and to be determined. You almost could have shortened that a little bit just by copying the problem, but I want you to learn to extract the crucial information and get it into your given and to be determined. So solution, I'll start that next. For a problem of this type, first thing you do is to make a sketch. You are given that, then a given and to be determined, and then free body diagram. Okay, I'm going to start with the free body diagram for the mass that's sitting on here, and so I'll have acting on it. The low-hanging fruit is always mg, and then I'm going to sketch in the angle that the plane makes. The tension is going to be straight up the plane, and I'll just write that as T1. It's the tension acting on mass 1, and I forgot a subscript of M1 on there. Then there's a normal force. The normal force is perpendicular to the tension, and then there's a frictional force. If the block is going to be pulled up the plane, the friction will point opposite that, going back down here. So when it's static friction, we're actually interested in overcoming static friction. And so we're going to max it out. Okay, the next thing, I write the sum of the forces acting on this one is going to equal 0. Because we're not accelerating it, we're just going to give it enough force so that a tiny bit more would nudge it and make it start moving. So we're just maxing out that static frictional force. Then if I write that, I just get N plus F sub S plus T1 plus M1G is equal to 0. Now, the next thing I always do is select a coordinate system and write these forces in I hat, J hat notation. And I've noticed people struggling with this, so I'm going to write it in a particular way this time so that it'll be easier for you to see how those work. But the first thing I want to do is select a coordinate system. Now, 3 of the vectors either point up and down the plane or perpendicular to it. One of them is at an angle to the plane. But to minimize work, I'll select a coordinate system that falls in with these 3 vectors here. Then I'll just let x point up the plane and y point perpendicular to the plane. So I have that. Now, I'm going to quickly make a sketch that'll let me solve for M1G more easily. And what I'll get here is there's M1G. Oh, need to make a sketch of the plane that I've got here. This is the angle theta. I'm going to avoid writing that as much as I can. This is theta. This will be 90 minus theta, and this will be theta again. And practice that if you're not good at doing that yet. Okay, I'll be able to divide M1G into two components, one of which is into the plane and one is down the plane. This one down the plane will be M1G sine theta, and the one into the plane, which I've run out of room to write things, but that'll be M1G cos theta. Okay, now I can write all of these vectors in terms of I hats and j hats. The normal force pointing in the same direction as y, and I'm going to do something here. I'm going to leave a blank space and just call that the magnitude of the normal force in the j hat direction. This is where I'm going to put I hat terms. That static frictional force is the next one I've got here. It's in the minus x direction, so I'd call it minus F sub s I hat. I'm not sure if I said that or not correctly, but anyway, minus F sub s in the I hat direction. The T, tension, is in the positive I hat direction, so it'll be T in the I hat direction. And then the weight here. This is something that I noticed people struggling with on the quiz last week, was recognizing that M1G was going to have a component in the minus y hat direction and a component in the minus j hat direction and in the minus I hat direction. So this would be minus M1G sine theta in the I hat direction and minus M1G cos theta in the j hat direction. Okay, now I can write my x and, whoops, I think we're losing you here. Yeah, I can write my sum of the terms in the x direction, the sum of the forces in the x direction, those are going to equal 0. Well, what have I got? I've just got t minus f sub s minus mg sine theta. So actually that's t1 minus f sub s minus m1g sine theta is equal to 0. So there's one equation. I didn't mean to write this line on here, but we'll ignore it for now. The sum of the forces in the y direction are also going to equal 0. What have I got? There's a j hat one, and there's a j hat one. So I just have n minus m1g cosine theta is equal to 0. So that'll let me figure out what the normal force happens to be. Time to start a new sheet of paper. On your solutions for the quiz, you didn't have to write all this, so you would have been able to squeeze all this into one page. I can simplify these a little bit further. And one thing I can do is that since I know the normal force and I know when F sub s is maxed out, it's equal to the coefficient times the normal force. In general, F sub s is less than or equal to mu sub s times n, but in this case it's the equality. So I can say that F sub s equals mu sub s times n. And n is equal to m1g cosine theta. And so you could just continue that and say mu sub s m1g cosine theta. And then finally, I can solve this T1 equation here for those other terms. So T1 will equal F sub s, plus, well, I'll just go ahead and write a longer thing here, plus m1g sine theta, which is equal to mu sub s m1g cos theta plus m1g sine theta. And that's as far as I can go just by considering block 1. But now I can start considering block 2. If I look at the forces on it, it's got an upward force of tension, which I'll call T2 because it's acting on block 2. And as a vector, this one is not equal to T1 as a vector, but it turns out magnitude-wise they're equal. Anyway, I'll also have M2G there. And with positive being upward for this one, now if I was worried about accelerations and signs of accelerations, I might pick positive to be downward for this one. But in this case, I'm not going to have acceleration. So I'll just say T2 minus M2G is going to equal 0. We're interested in the instant before acceleration starts. So the T2 is just equal to M2G. And T2 is equal to T1, and I'm just going to call that T. So there's an expression for T2. M2 is the thing I don't know that I'm trying to solve for, but I can take this expression for T1 and just set it, replace T1 with T2 here. So I can say M2G is going to equal mu sub s M1G cos theta plus M1G sine theta. Okay, what else have I got? Well, there's a G in every term, and so I can knock those out, and I'll have the M2 that I need. And then let's see, if I cross out the G's here, I've got M1 in both of these. So I can say it's going to equal M1 times mu sub s cos theta plus the sine of theta. And just for the heck of it, when I calculated these, I kind of split them out, and this part here was equal to 0.35 when I plugged in the numbers. This part here was equal to 0.595, and when I combined them together, only 2 sig figs on this one, I ended up with 0.94. And so usually I would just plug all of these in at once. In fact, I did that first, but 0.94 M1, which is 0.94 times 2.53 kilograms, and M2 ends up equaling 2.4 kilograms. I only have 2 significant figures on it, but that's the way that it happened to come out here. And so that would be the minimum mass that you need to just barely max out that frictional force. And if you go beyond this, stick another 2-gram pieces on top and it'll probably start to slide. That was the solution. Now, something I'm going to do with this problem is convert it into a PDF with my phone, and I'll post that to show you what a good PDF should look like. I've gotten some PDFs submitted that are unreadable, so I'm gonna right now I've got a nicely lighted surface, but I'm just gonna take this down to our kitchen and photograph it sitting on the counter so you can see what you should be able to do to make a good PDF at home.